Hi, everyone. My name is Jacob. Thanks for joining me today. Today, I'll be talking about a survey that we did based on genetic algorithms and how they're used in industry, in engineering workplaces. So the title of our paper is The Journey, Not the Destination. And uh, first thing I wanted to talk about was human-driven design. And I want to take a look at the picture on your screen, and you can see that there's a whole bunch of people all working around engineering drawings, and you can see all the tools that the engineer right there in the forefront is using rulers, pencils, paperweights. He's even using a mat for his knees. So he's trying to get as comfortable as possible, and all those tools there are there to support him in his task. And what's really interesting in this picture is that there's no computers, and every single decision and every single design decision is made by a human. And what's good about that environment is that most of the time is spent on value added tasks. So every time an engineer is making a change to a drawing or making a new drawing, they're adding value to their product. And essentially, this is what we pay engineers to do. We pay them for their expertise and their knowledge and to produce new products and new designs. And the most important thing at the end of the day for these engineers is to be able to justify their decisions and to why they made their decisions in the way they did. They have to justify it to themselves, to their colleagues, and sometimes they even have to justify it to regulators. And so while it seems like a long time ago that this is the way that engineers worked, it actually wasn't that long ago. And there's some pretty special projects that were made this way, including one by Lockheed Martin. And they made a very special plane using just drawings made on paper. And that is this plane right here, the A-12, which is the predecessor to the SR-71. So this plane could cruise at Mach 3, which is 3 times the speed of sound, and it could go higher than any plane before it. And what's incredible is it was done all by it was drawn all by hand, and no computers were involved in making it. And this really was a process for designing a lot of planes, was that a lot of humans were involved and very little computer involvement was made. Over the years, as certain technologies evolved, uh, certain optimization techniques were also introduced. And so as wind tunnels were made, aerodynamic performance was increased through that. As computers got better and faster, the introduction of computational fluid dynamics helped optimize the design. And then now the latest way to optimize designs is automated solution finding. So asking the computer to find the best result using CFG, and it iterates over and over again. And one of the ways that it iterates, or one of the algorithms that it uses, is genetic algorithms. And they're very powerful. So they are able to look at a whole population of potential solutions and then find the best ones. Um, then it selects the best ones, and those keep going, those get better and better, and it discards the solutions that aren't good. There's a whole host of genetic algorithms that are available, including the one based on the bird in the picture, the cuckoo algorithm. These algorithms are then tested in a variety of scenarios. In this case, the camel represents our genetic algorithm, and it's put against different benchmarks. These benchmarks include mathematical functions or engineering benchmarks, such as a pressurized vessel or cantilever beam. They're very simple, but they are there to prove the efficacy and accuracy of these algorithms. Unfortunately, by going for these benchmarks, the developers of genetic algorithms fall into a trap, and that there's no free lunch. And it goes on for the no free lunch theorem. This theorem states that for every one thing that an algorithm gets better at, it gets equally worse at another. And so a lot of the work is done on improving these algorithms just for these benchmarks. Well, at the same time, they're getting worse in another area. And a lot of the work is also done on improving these algorithms, not for any practical purposes and only for these benchmarks. And so what we wanted to do was to see how we could introduce these algorithms into industry in a way that would matter to practitioners. And that leads us to our 2 research questions for the paper. So to what extent is there a pre-existing sentiment, negative or positive, among students, engineers, and managers towards genetic algorithm-based design? And what are the requirements of practitioners with regards to design optimization and the design optimization process? Really, we wanted to find out what's preventing engineers from using these algorithms, and then where could these algorithms be best placed in the design process. So we conducted a survey that had 3 parts. The first part was finding non-identifiable traits, such as their experience and their current job. The second part found out their prior knowledge in the domain. And the third part was 6 optional open-ended questions that the participants could answer, either all of them or none of them, or a mixture of the 2. We've got 23 participants, which were a variety of students, engineers, and managers. In fact, we got 9 students, a researcher, 8 design engineers, 7 other engineers, and 3 managers. And we have a variety of experience levels, including 7 with more than 10 years of experience in the field. And 83% of them said they were either proficient, very proficient, or extremely proficient in engineering design. On the open-ended questions, we use thematic analysis, actually reflexive thematic analysis to be more specific. And what it does is it groups similar answers together in for qualitative analysis. And by grouping similar answers, we can link these answers and find common themes. The 3 main themes that we found in the answers were to do with people, and so how the design optimization process and how these algorithms affect people, how they affected the product that they were designing, and how what kind of technology they were using during their design optimization process. Based on the answers that participants provided, we came up with 4 recommendations to try to enhance or increase the uptake of these algorithms in industry. And the first was designing trust and how to improve trust in these algorithms. There was many answers that indicated that there was a lack of trust in these algorithms, and not only in the results of the algorithms, but also in the process. So because certain engineers or designers couldn't see how the algorithm was behaving or what results it was giving out, they couldn't trust it. And if they couldn't trust it, then they wouldn't be able to justify their decisions. Another key thing that came up was job security. It's important for us as academics when we design these algorithms, or developers when they design these algorithms, is to note that we're not trying to remove human from the design process. These should be tools that support them the same way that a ruler does, or that map did. And we can also build trust through explainability and transparency. Another key takeaway from the survey was that the user interface was the most important factor in an engineering design tool. We don't want engineers to be stuck with a program that takes too long to set up or that has a lot of technical issues. And they really should be tools that allow them to do their job better. And if these tools don't have any problems in them, then they can the engineers can focus on the value add activity, really what the engineers are paid for. The third recommendation was that there should be an increased level of communication between developers and engineers, and it should be a 2-way feedback loop system. What this does is it sets the stage for developers to take ownership of their algorithms and also the claims that they make for these algorithms. So some developers claim that their algorithm is the fastest. They should really state where, in which scenarios these algorithms perform best. And so what are the advantages and limitations of each of these algorithms? Lastly, we want to talk about visualization and how it can be used to enhance trust. In a 2006 paper published by the American Psychological Association, visual learning proved to be the greatest form of information gain, regardless of perceived style. So some people think they learn best just through audio, some people through visual cues. Regardless, visualization is the best way to get the most amount of information out of something. And so we think it's an excellent way to provide a level of explainability and transparency for these algorithms, and thereby building trust in these algorithms. And because if it is then able to be explained and transparent, the engineers will then be able to justify their decisions to themselves, to their colleagues, and then lastly, even regulators. And while algorithms and humans are two separate things that I talked about, really, I think the optimum of design lies at the intersection between humans and machines. Thank you for listening, and on screen a QR code for our paper.